الرحيم. الحمد لله والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. نرحب بكم في اليوم الثاني من فعاليات مؤتمر الكيمياء الدولي في الكيمياء التطبيقية، ويعني موعدنا الآن مع محاضرة كان يفترض أن يلقيها بروفيسور توماس ويبستر من جامعة نورث ويسترن في أمريكا، ولكن للأسف الشديد قبل موعد رحلته سيارة صدمته وعنده مشكلة في رجله الآن. واليوم دكتور نظير الدين is volunteered to give a plenary lecture instead of Professor Thomas Webster. Professor Muhammad Nazir al-Din received MSc and PhD in inorganic chemistry from Osmania University, Hyderabad, India. He joined as a lecturer in Dekan College Engineering and Technology, Osmania University in 1986. And subsequently moved to Central Salt and Marine Chemicals Research Institute, Bhavangar, as a research associate. He was awarded the Government of India Indian Fellowship in 1987 for study abroad. After 1 year postdoctoral stay with Professor Grazil at Swiss Federal Institute of Technology, Lausanne, he joined the same institute as a senior scientist. His current research focused on dye-synthesized solar cell, hydrogen production, light-emitting diodes, and chemical sensors. He has published more than 380 peer-reviewed papers, 10 book chapters, and inventor of 40 patents. The high impact of his work has been recognized with innovations to speak at over 80 international conferences, including the MRS Fall USA 2006 and Spring 2011, Meeting Gordon Conference 2014, and has been nominated to the OLA International Scientific Advisory Board. He appeared in the ISI listing of most cited chemists and has more than 33,500 citations with an H index of 89. Nazir, I suppose this is old one. He is teaching functional materials courses at EPFL and Korea University, directing and managing several industrial, national and European Union projects on hydrogen energy, photovoltaics, DSC, and organic light emitting diodes. He was awarded EPFL Excellence Prize in 1998 and 2006 Brazilian FAP ESP Fellowship in 1999, Japanese Government Science and Technology Agency Fellowship in 1998, Government of India National Fellowship in 1987 to 1988. Recently, he has been appointed as World Class University WCU Professor by the Korean University, Joshua, Korea, and Adjunct Professor by King Abdulaziz University, Jeddah, at the Center of Excellence for Advanced Material. Nazir, please give us your talk.
Good morning, ladies and gentlemen. First of all, I would like to thank the organizing committee for inviting me, particularly Professor Abdullah Siri, for putting together such a very nice, excellent conference. The weather here is fantastic. Coming from Switzerland to this place, you come from 10 degrees to 26. It's very nice weather, and then the daylight is brilliant. Now, I come back to my title, Prospects for Perovskite Solar Cells. This slide is abstract of my presentation. As you can see from here, we started working on the Dyson solar cells, ruthenium complexes, cobalt redox mediators to get highest efficiency. Using this combination of ruthenium sensitizers, cobalt redox mediators, the highest efficiency you can obtain is 12%. Further, we modified these sensitizers to a new class of sensitizer. This molecule is highly trilid molecule where we have incorporated all the interesting properties learned through the years of our experience. So if you take this one, yesterday Professor Hackfeld has mentioned that this particular alkoxy substituted donor group is very important. It reduces the recombination. Look at this chromophore. And this chromophore is highly designed why we should have a alkoxy substitution at 2,6 position, 2 and 6 position. Why can't we have it here? No, if you have there, the problem is it enhances the recombination. Only these particular positions are very important. And if you see the molecular modeling on the surface of TiO2, it clearly demonstrates that it influences on the recombination kinetics. Well, if you look at this unit, is it necessary? Yes, it's very important. It's very vital. This is an electron acceptor unit. It's called benzothiazole. If you don't have this phenyl group, what happens? The difference in the efficiency, having phenyl and without phenyl is order of magnitude difference. The reason is, once if you inject electrons, the electrons, they come back to the benzothiazole group. So you separate by putting the phenyl group. So for you, it looks very simple, but it's a very highly designed molecule. Having the phenyl and no phenyl influences order of magnitude in the power conversion efficiency. Of course, this is the anchoring group. So using this type of sensitizers, we obtained 13% efficiency. You can see more work in Nature Chemistry. This paper is highly cited. Since 2 years, we are working on the new pigment, new sensitizer, replacing all these type of sensitizers, which has a lower molar extension coefficient. I'll come back to this point later stage. Perovskites. This material is really making a lot of headlines because of its high power conversion efficiencies. I would consider this material as a poor man's silicon technology. With this material, with a minimum investment, you can get the power conversion efficiency as good as silicon solar cells. If to give you a reference, silicon solar cells gives you efficiency of 25%. And this material is already reaching 21%. And further optimization, you can reach very close to silicon cells efficiency. I also have interest on the light emitting diodes. People who are using mobile phones, they all use this technology, light emitting diodes. Eventually, we want to get rid of this high energy consuming lights by this white light to reduce our energy consumption. To do this one, you need a material. You need 3 fundamental colors, blue, green, and red. In the market, you have a green color, which goes up to 10 years guarantee. You have a red material, which also gives you 10 years stability. Coming back to the blue emitting phosphorescent material, they are not very stable, but you don't recognize because you don't use your mobile phone more than 3 years. So eventually, if we want to go for the technology, which is more than 10 years, we have to have a highly phosphorescent blue emitting material, green, which is known in the market, which we have now, red emitting materials, to get eventually the white light emission coming from this one. You can have a display applications also. So I'm working at École Polytechnique Federal Lausanne. I'm a world-class university professor at Korea. Of course, I have affiliation with King Abdulaziz University. I had affiliations with the King Saud University, eminent professor at Brunei University. This is our campus, very beautiful campus. You are all welcome to visit our campus. And we have a very nice mountains, Alps, on the other side of the lake. And this is the lake. It's not like a Red Sea, but it stretches between Geneva and Montreux, around 65 kilometers, 20 kilometers width. Now, I have simplified the perovskite solar cells into components. So, deposition methods. What is this perovskite materials? I will give you the materials properties and deposition techniques. And then we go absorber layer modifications. How we can modify these materials? What are the properties we can modify? How can we understand this material? And hole transporting material, electron transporting material. The beauty of this material is you have a perovskite, a block of material. It absorbs light and it gives you the electrons and positive charges. And this block of material, like a highway for electrons as well as positive charges. Now what you have to do is, you have to engineer materials that extracts these positive and negative charges selectively. That's all you have to do that one. So in my presentation, what we are going to see is how I am going to engineer the materials that extracts exclusively positive charges and extracts negative charges and without getting the recombination. So I have to give you some background. Without giving the credit, I cannot say this is my material. But the beauty of this material is nobody has a claim on this material. This material is known since 1978. A Nigerian scientist, he first discovered this material where he has used lead iodide, potassium iodide, he mixed it together, he found excellent absorption. And then he predicted, he published this one in Solar Energy Materials. He predicted this material will be excellent solar absorption material so that it can be used for power conversion efficiencies. In 1980s, David Medji from IBM, he started working on these materials for optoelectronic applications, where he has used extensively for transition applications. 2009, Tom Miyazaki, one of his students, they jointly applied this material as a sensitizer in dye-sensitive solar cell. They obtained 3.9% efficiency. That was the starting point of the perovskite material. Now, coming back to the perovskite material, it's a simple mineral. And the perovskite, the name came, well, the fact because the material was discovered in Russia and named after the famous geologist Perovsky. This perovskite material is typically having ABX3 formula. A is a monocation, B is a dication, X is a halogen. Now, in this ABX3, you have enormous opportunities to tune A, monocation, you can tune B, a dication, and X halogen from fluoride, bromide, iodide. That gives you opportunity to have your absorption spectra anywhere between 400 nanometers up to 800 nanometers. That's what you will see in my presentation. Another interesting property of this material is a strong absorption, high molar excitation coefficient. What does that mean? If you take any ruthenium complexes or organic sensitizers, they all have a typically between 10 to 30,000 molar excitation coefficient. Here, these materials, they are comparable to any thin film solar cells which are known in the literature. The optical density absorption, the attenuation power of this material is huge, so that for ruthenium or other sensitizers, the thickness of the film is few micrometers, typically 10 to 15 micrometers, to attenuate all the light. Here, you can afford to reduce the thickness to less than 500 nanometers. 500 nanometers of thickness of perovskite can attenuate all the visible light hitting to the perovskite material. So I have highlighted some of the very interesting properties of these materials as shown from top to bottom. It has a sharp onset, like this one. Any other organic molecules, inorganic complexes, have a tail that's coming from the forbidden transitions. But in perovskites, you have a strong onset. This have a separate applications for tandem configurations, where you absorb selectively visible portion and then leave the near IR portion to some other cells so that you can combine the power conversion efficiency of visible absorbing perovskite and near IR absorbing silicon solar cells. Now, they have a electron and conductor. The charge mobility of this material is extremely high. Right, charge mobility. If you look at the organic molecule, you excite, you create a positive charge, negative charge. This we call exciton. This exciton, they go like a pair everywhere. To separate this exciton, where positive and negative charge is going together, you need a minimum 300 milli-electron volts, right? The beauty of this material is the moment you excite this perovskite material, the electron and positive charges, they dissociate. Why is it so? This is very interesting question. We are still understanding the properties of this material, but I can give you my point of view. I have a water somewhere. Yeah, let me just take this out. So the reason why this material has a very low exciton binding energy is because this is highly symmetric material. Reduce it to a molecular level. Lead and hexaiodide. It's a lead as a central atom. It's a hexa-coordinated metal, the complex. What happens is all the valence band of this material is dominated by p orbitals of the iodide, and all the LUMO levels are dominated by p orbitals of lead. Now, if you excite this 3D-dimensional material, you remove the electron coming from the valence band to the LUMO level, but because of the electron donation coming from the 6 iodides, and that dissipates positive charge in the 3-dimensional matrix. Thereby, the electron which has just gone into the LUMO, that doesn't recognize anymore where the positive charge is. So the positive charge has dissipated into the matrix. Similarly, the electron also is dissipating in the LUMO levels of the p orbitals. This way, the recombination of this material is non-germinate. That means if they recombine, the electron and positive charge are not coming from the same family or same center, can be somewhere else. That's how the recombination, the binding energy of this material is as low as 20 millielectron volts, and people are calculating even lower. Now, that's what I have discussed. Another interesting property of this material is the beauty of the electronegativity. The planet is surviving because of water. The electronegativity difference between hydrogen and water is very small. And in this lead perovskite, iodide has a 2.66 electronegativity, lead has a 2.33. Such a small difference in the electronegativity creates a beautiful combination of ionicity and covalency. If you take the covalency, methane is a covalent bond, sodium chloride, ionic bond. So here, the beauty of this material is you have two properties joined into the same material. And not only this ionicity covalency, which is helping, it comes on the sixth row metal. You have a f orbitals, and then you have a heavy atom effect, spin orbit coupling. All these parameters is as helping these perovskites to behave the way these properties we are seeing now. So the charge collection, you can have these materials, charges collect over the range of couple of micrometers. So the lifetimes are quite high. I come back to the device. So we have seen Dyson solar cells yesterday, Professor and the Cypress talk. What we are doing is we are just taking a same configuration, not liquid electrolyte, but going a solid state Dyson solar cell. So this is a solid state Dyson solar cell configuration where you're having a conducting glass. This is a blocking layer. You have a titanium dioxide nanoparticles. You infiltrate the perovskite and the whole transporting material. This is a contact. Typically, we used to have efficiencies between 7 and 8 using this type of organic sensitizers, this type of whole transporting materials, pyrovometide. In the perovskites, the mechanism, there is still controversy. Some people consider the perovskite like a Dyson solar cell, some they don't. But in any case, for understanding, let's consider this as a Dyson solar cell configuration. So you have a perovskite, you have a TiO2 conduction band, you excite, the electrons are in the conduction band, it injects electrons to the TiO2 conduction band, you extract. So I call these electron selective layers. The positive charges will be extracted into whole transporting material like this one. So what you will see in my presentation is what are our efforts to improve the efficiency to get discharge collection efficiency as good as possible and electron injection efficiencies. There are several cell configurations. I have highlighted here two types of cell configurations. One, mesoscopic perovskite solar cell. This one, what does it mean, mesoscopic? So what you are doing is you are depositing 200 to 300 nanometers TiO2 nanoparticles, and you are infiltrating the perovskite through the nanoporous material. The other one is a planar configuration, where you are having a flat conducting glass, and you deposit 300 nanometers of the perovskite layer and hole transporting layer, then contact. In this configuration, you can also have a NIP, PIN configuration. It all depends where you are putting the hole extraction and electron extracting layers. So now I come back to the deposition techniques. So there are several techniques, but I have highlighted here it's 4. This is a one-step method. First, let me give you what is perovskite. The perovskite is simply you buy lead iodide, methylammonium iodide. These are commercial materials. You mix in 1:1 ratio in either DMSO, DMF, gamma butyllactone. You get a perovskite solution. You spin coat it the way is shown here. You spin coat it, heat it at 110 degrees, you form the perovskite. The technology is so simple compared to silicon solar cells. This is very easy material. Second approach we have taken is a sequential deposition. First you deposit lead iodide, and then you put this lead iodide containing electrode into methylammonium iodide solution. The condition here is you have to select the methylammonium iodide solution in such a way that the formed perovskite is not soluble in the solvent. So in this case, isopropanol, you take methylammonium iodide, you bring lead iodide containing electrode, dip into methylammonium iodide containing isopropanol, you get the perovskite solar cell. The third technique is sublimation. You take lead iodide, methylammonium iodide, you sublime at different temperatures, you form the perovskite on the surface of your substrate. So this is a very easy way of forming the perovskite films. The fourth one is a combination of solution followed by sublimation. In my presentation, I will be focusing on these three to give you what is the state of the art. Look at this figure. We have published this work in Nature Photonics in collaboration with Dr. Sok. We have a conducting glass, mesoporous TiO2 nanoparticles infiltrated with perovskite. This is a polymer. So polymer doesn't infiltrate into the porous material. The beauty of this material is demonstrated already here. When you shine the light here, perovskite injecting electron into the TiO2. And the positive charge are traveling all the way from here up to here, extracted by hole transporting material, demonstrating perovskite not only strongly absorbing, but equally it is transporting positive charges from over the distance of 600 nanometers, right? And Henry's group, he has used, instead of titanium dioxide nanoparticles, which has a lower conduction band than the LUMO, the electrons also transported, saying that the perovskite material absorber as well as positive charges transporting material and electron transporting material. Using this, you can see the band alignment here. The power conversion efficiency is what we have obtained was at 12%. This is a typical IV characteristics. This is IPCE spectra of this perovskite solar cell. This work is published in Nature Photonics. You can see more details. Here, this diagram shows you the problems associated with this perovskite solar cells. Reproducibility is not very high. To overcome this reproducibility problem, we have introduced this sequential step method, where you deposit first lead iodide, followed by methylammonium iodide, you get the perovskite. This work is highly cited over, I think it's exceeding 2,000 times the citation of this paper. We published it in Nature. The work is, the cross-section image of this work is shown here. You have a conducting glass, perovskite infiltrated with the TiO2 matrix, whole transporting layer, and gold as a contact. Now the question is, are we infiltrating the perovskite through the mesoporous layer, or we're just forming a layer on the top of TiO2? Here, the elemental mapping of lead clearly shows that the perovskite material is infiltrated through the porous material, and they all are connected through the porous network. The efficiency we reported was 15%, and then further, finally, we certified at Newport. So the third method is a sublimation technique. This gives you power of controlling your film thickness. Not only film thickness, you can have a plastic solar cells, whatever substrate you want, you can use this one. And the reason is, at the substrate where you are subliming, the temperature doesn't go more than 80 degrees centigrade. So you can control the film thickness by the time of evaporation. So this is the dual source method. This work was published in Nature Photonics 2014. Why? The beauty of this system is inverted configuration. Before, we were shining the light through the N side, and now we are shining the light through the P side. You have a whole transporting material, that's a poly-TPD. You have a perovskite block of 285 nanometers thickness, which absorbs all the light. You have a hole blocking layer. In other words, an electron transporting layer. That's a PCBM. So what we are doing is, we are replacing TiO2 as electron transport material by PCBM material. So the band alignment is shown here. I say poly-TPD. The valence band of the perovskite is minus 5.4. The poly-TPD valence band is close to minus 5.3, minus 5.4. So what you are having is, you have very well aligned HOMO of the perovskite and HOMO of the whole transporting material. Look at on the other side, the LUMO of the perovskite is minus 3.9, and the PCBM is on the same region. Now, here what you are having is, you have a block of perovskite, you excite. Now, it doesn't matter where you put positive charge, whole transporting material or electron transporting material. The electrons and holes are like a highway, they are migrating everywhere. Only thing is, what you have to do is selectively put the HOMO level so that you extract positive charges and put the electron acceptor layer to get the electrons extracted. So this band alignment is very vital. Last two slides, I will show you the importance of the band alignment. So this power conversion efficiency at that time, it's 12%. These are the typical IV characteristics. This is IPC spectra of this particular device. Now come back to the perovskite layer itself. What we can do for the perovskite layer? I mentioned that the composition of the perovskite is 1:1 ratio of lead iodide, methyl ammonium iodide. Is it the correct ratio? So what we have done is, very systematically, this work is really a joint work between involving several people in our group and several professors. I show you the last slide. It's a teamwork. But let me give you, for you, the information take-home message is, lead iodide composition, if you want to start the perovskite solar cell, lead iodide composition, you should have at least 5 to 10% excess of lead iodide when compared to methyl ammonium iodide. This is the take-home message. Now look at the data. You have a 1:1 methyl ammonium iodide, lead iodide ratio, efficiency close to 16%. So these are the three parameters which are very vital to get the power conversion efficiency, current, VOC, fill factor. So if you have a 5% excess of lead iodide, the efficiency goes up to 17%. If you have a 10% excess of lead iodide, efficiency goes to close to 19%. Now if you go 15%, it starts decreasing. See the beauty? So when you have an excess of lead iodide, it's giving you high power conversion efficiency. Now the question we have to answer is, where is this lead iodide? Is it in the bulk of the perovskite? Is it in the interface between the TiO2 perovskite? Or is it in the interface between the whole transporting material and perovskite? So the findings are still unraveling, but I can give you some hints where these can be. So this slide shows you the final optimized data of 15% excess lead iodide, which is 19.1. This publication is already online. AES, if you want, you can get more details. This is corresponding IPC spectra showing the current which you are generating here. It corresponds to this IPC spectra. Our efforts to understanding this material. This slide shows you a 1:1 ratio of lead iodide, methylammonium iodide. Now I can shine the light through the whole transporting material side, or I can shine the light from the TiO2 side. So the lifetime of this perovskite material, if I shine through the top layer, let's say from the perovskite side, 23 nanoseconds. If I shine the light from the TiO2 side, the lifetime is 18 nanoseconds. Same thing, now I'm increasing the ratio of lead iodide, increasing from 0 to 20%. If I'm shining the light from the lead iodide side, the lifetime is decreasing significantly. So this gives me only a hint, it's not proven, hint that's showing that the electron injection is enhanced significantly when you have a excess of lead iodide. What is it doing? Is it is modifying the interface between the TiO2 and the perovskite. This is one possible speculation, and that supports when you shine the light from the lead iodide side. And here is the luminescence properties. This is 1:1 ratio. You go 5%, 10%, 15%. So you increase the luminescence of this material, modifying the interface properties of this lead perovskite. Another important findings, so this work will be online very soon in Advanced Materials and Advanced Energy Materials, 2 papers. One, where we are having, you have taken the lead iodide, methylammonium iodide, 1:1. Now, can I dope with the excess of lead bromide in this combination? So that's what data is shown here. So black curve is the reference where 1:1 lead iodide, methylammonium iodide. 1% excess of lead bromide as a dopant in this material enhances power conversion efficiency significantly. Why it is enhancing? Now we took this surface analysis. Without any lead bromide, the crystals are like a crummy, puffy. If you have a 1% lead bromide simultaneously or 1% lead chloride, the crystals takes shape, very defined shape. You can see this one. So this 2 works with the lead iodide dopant, lead bromide dopant. You will find more details in Advanced Materials and Advanced Energy Materials publications will be online soon. Perovskite materials are inorganic salts. They are unstable. They are highly hygroscopic. Now you have to come up with some approaches how you can stabilize these materials. Can we put some dopants inside that binds this material? So one approach we have taken is, we have taken this additive, phosphonic amino butyric additive, and that by adding these into the perovskite, what we think is the perovskite pillars are enhanced by this linker molecule. So the configuration is shown here. You have FTO, blocking layer of TiO2, mesoporous TiO2, perovskite is infiltrated, cold transporting material spiro, gold as a contact. Now, question is this linker is going in the whole perovskite material or it's somewhere on the surface? EDX analysis and elemental mapping clearly demonstrates that the phosphorus mapping showing that this additive is everywhere in the perovskite. You can see from the lead mapping and titanium mapping and phosphorus mapping. These are the corresponding NMR details. If somebody is interested, I can explain later. But let's go to the influence of this additive, why we have added. What is the influence of this additive? If you look at this one, this is a pristine 1:1 lead iodide methylammonium iodide. This is with additive. The absorption properties has increased. Now this is the IPC spectra, pristine and with additives, and this is corresponding IV characteristics. Power conversion efficiency having additives is close to 16% or 16.5%, and without any additives we have only half of that one. And another beauty of this material additives is the stability. This is the pristine material stability, over the period of 1,000 hours, you can see even at 100 hours, it's coming down significantly. In the case of additives, it's relatively more stable. So 90% of the stability you can get by this material over 300 hours of exposure. As I mentioned, the perovskite is a beautiful material having ABX3 formula. A is a monocation, B is a dication, X is a halogen. So now can we change the A cation? Perovskite is a tetragonal material. The ammonium cation it goes into the porous of this material. If we change from ammonium cation to formidinium cation, the formula is shown here. This is methylammonium, CH3NH3, and the formidinium is NH11CHNH3. If you just change the cation, you can see the properties. This is pure methylammonium iodide perovskite, which has the absorption maxima very close to 760 nanometers. And if you take the red line, which is a pure formidinium iodide perovskite layer. So what we are doing is we are just replacing the cation from methylammonium to formidinium. You can see the changes in the absorption properties. Now, since you know this property, you can mix with the different ratios to tune your absorption properties depending on the ratio. This is a 3 times methylammonium and 1 time formidinium. This is 3 times formidinium, 1 time methylammonium iodide. You can have various ratios to tune the spectral properties. Using this mixture, 860 to 40% methylammonium iodide to formidinium. Formidinium is a 40% cation. 60% cation is methylammonium iodide, but the perovskite is the same lead iodide. We got 14.9% efficiency. We published this work in 2014. Making use of this combination, Dr. Sok, he has changed the composition from methylammonium and formidinium, and instead of having pure iodide like what we did, and he has changed the anion also. 85% iodide, 15% bromide. So what does this bromide composition does? Because of electronegativity, and these bromide perovskites are much more stabilized compared to pure iodide perovskite. So you are increasing the stability of this perovskite without influencing significantly absorption properties of this perovskite because the contamination is only 15%. The power conversion efficiency which he has reported using this combination is 18.4. He has certified this efficiency. These are genuine numbers. Yesterday, Professor Anders Hackfeld has shown this one. This is the work which we got at EPFL. It's his postdoc. The current which we got is 24 milliamps. By using same composition, but added excess of lead iodide, which I have shown you in the composition. So we have used the perovskite composition of 85% 85% of methylammonium. Let me take it correct. 85% of formidinium iodide perovskite, 15% of methylammonium bromide perovskite with excess of lead iodide gives you 24.2 milliamps current and 1.12 voltage, very close to 20% efficiency. This has been certified, and this work will appear in Science Advances in coming weeks. I come back to another very interesting topic. I have taken this from literature to show you what is going on in the perovskite field. Look at this diagram. You have a conducting glass, mesoporous TiO2 layer, and overlayer. This overlayer is a very interesting concept. So how do you get this overlayer? When you spin coat, before drying totally, you drench with some solvents which are precipitating, for example, toluene or benzene. You can drop before you dry that one. And that gives you this overlayer thickness. So, in other words, you have created 2 perovskite solar cells, as I mentioned in the beginning, mesoporous perovskite solar cell as well as a planar heterojunction perovskite solar cell in a single go. But the problems with planar junction perovskite solar cells, as well as sometimes in mesoscopic perovskite solar cells also, the hysteresis. When you have a scanning from the a reverse scan and a forward scan, the IV characters are not the same. Right? What are the reasons of this? So, in the literature, there are several speculations. The first one can be it's a surface interface state acting as a slow drops. This is one possible reason. The ferroelectricity. If you take the perovskite as a three-dimensional material, the cation is fixed in the pores of the perovskite. So this cation can change its polarity. It can rotate. This can create the ferroelectricity. That's the one possible reason. The migration of interstitial ions. So even though perovskite materials are very nice, but in a bulk, you may have a defect. And if you take this as an octahedral symmetry, you may have a defect in the axial position. You may have a defect in the plane. So if you have a defect in the axial to axial migration of anion can cause this problem, or plane to plane also can have a ion migration or cation migration also. But there is that I show you the 2 slides later. Another interesting aspect of this can be imbalanced charge extraction. As I mentioned, the perovskite material you extract, you have your positive charges and negative charges. What happens if you extract all the negative charges and leave some positive charges unextracted? This may create this hysteresis problem. So our work shows that this can be one of the reasons that this Kelvin force microscope measurements clearly demonstrate that electron injection is much faster than the positive charges extracted into the Hole transporting material. In other words, you have an accumulation of positive charges on the interface between the perovskite and Hole transporting material. So this is another beautiful work coming from UK, Bath University. So this is the vacancy of the iodide. So this iodide can migrate here, or lead can also migrate, or cation can also migrate. But the chances of iodide, the energy required to migrate iodides are smaller than lead migration because lead is involved in hexacoordination. I come back to the Hole transporting material. It's because, as I mentioned, charge extraction is an issue. Okay, charge extraction is an issue. So now can we solve this problem by engineering materials to synthesize so that you can extract positive charges equal speed as electron injection? Towards this goal, the another possible reason for doing this effort is the stability of the spiral is very poor, and the price is very expensive, and synthetically it's very challenging. To give you information, only Merck supplies the material which are slightly higher, gives higher efficiency than other suppliers. Mobility is a problem in this material, so you have to dope it with cobalt complexes or any oxidant so that you create positive charges so that the mobility can be very high. To overcome all these issues, we have designed a very interesting molecule. Here again, the concept is to design molecule that has a bifunctionality. One, extract positive charges from the perovskite. Second, contribute in the near IR absorption where the perovskite is not absorbing. That was the goal of this material design. So as you can see, this flattened donor unit, it transfers the positive charge, and by putting the electron acceptor unit, benzothiazole, and the donors, you create the charge transitions in these molecules. And as you can see from the normal Hole transporting materials, they are practically colorless. And this new Hole transporting material absorbs up to 700 nanometers. This is one of the goals which we want to go, and even we want to go up to 900 nanometers. So this is the cell band alignment diagram. You have a TiO2 conduction band and the perovskite conduction band. The Hole transporting material HOMO is well aligned with the perovskite. The efficiency, what you see, is lower. But if you look at the importance of this data, 12.8% efficiency, this is highly significant for us because this data was obtained without any dopants. All 20% efficient data was obtained with the dopants which is incorporated into the spiral. So the first time we have achieved a dopant-free Hole transporting material that gives you 13% efficiency. Under similar conditions, without dopant, that gives you the Spiro 7.6% efficiency. This work is published jointly with KU, Professor Abdul Asiri, where the similar goal, you use this donor as a whole extracting layer and use squalene, which is a highly absorbing chromophore, to get the near air absorption. So power conversion efficiency, this is the spectral properties. So we have pushed significantly absorption maxima, and then the optical properties, that's a molar extension coefficient, is in the range of 250,000. It's a very high molar extension coefficient. So these are the spectral properties of the total cell, IPCE data, and this is the IV characteristics, take-home message. With these materials, you can reach 15% efficiency, the perovskite solar cells. Now, if you look at the polymer chemistry, the stability is always the polymers having silicon groups are more stable than polymers without silicon substitution. We took that information and we incorporated it into our whole transporting material. This work is online. You can read most of the synthetic details there. So let me just give you the IV characters. This is the IV data of using this new whole transporting material. This is IPCE. Though power conversion efficiency is still in the range of 15%, but the beauty of this material is stability. If you look at the normal spirometad, the stability is 1,000 hours, and if you look at the silicon-doped new whole transporting material, the stability is 6,000 hours. Another interesting material, very recently we developed, you have a perovskite. Now the perovskite can terminate with iodide ends. It can terminate as a P ends. If it terminates through iodide ends, now you have a possibility to tune interface materials that interact with the perovskite so that the positive charges can be extracted more efficiently. Look at our design. So this molecule with the donor groups and sulfur groups. Now, if you look at this, the Spiro, which is here, the interaction between the Spiro and perovskite is only weak interaction through oxygen and perovskite. In the case of new whole transport material, you not only have a interaction between the oxygen and the perovskite, now we have developed a very strong interaction coming from the sulfur and iodides. And this gives you a power conversion efficiency of 20.2. This is the highest when compared to spirometad. And this work will appear in Nature Energy first issue of 2016. What you have is very nice IPC data, current going up to 23 milliamps. On a relative scale, the Spiro gives you 22.7. The difference is not very significant, but the beauty is a new whole transport material that molecularly engineered that gives you 20.2% efficiency. I come very quickly on the electron transport layers. As I mentioned, the perovskites are very delicate material. They take humidity and then they destroy. Can we stabilize by imprisoning these perovskite materials in nano containers? That's what we have taken approach here. The nanotubes, we have taken 300 nanometers of nanotubes with 80 nanometers diameter. We infiltrated the perovskite inside the nanotubes. This work is online in small journal. What you see is you grow the nanotubes, infiltrate the perovskite in the nano containers, and if you look at the stability, I'm comparing on the same scale. I have made a solar cell, perovskite solar cell, using nanoparticles of 300 nanometers, nanotubes of 300 nanometers. And the nanoparticles one, that's a red one, is sealed with a sealant, special sealant, and the nanotube one is unsealed, just as prepared. Now, if you compare the stability over the period of 170 hours, they are almost overlapping, demonstrating our approach that you can contain this the perovskite in a nano containers, and then you can enhance its stability significantly. And the remaining data is similar as before I showed. So this is a nanotubes IPC, IV characteristics, and this IPC spectra of comparison between the nanoparticles and nanotubes. The efficiency with the nanotubes is 15%. band alignment is very important, very critical. So TiO2, people when they take the nanoparticles, the conduction band is different. When you deposit this material through ALD, by ALD deposition, the TiO2 conduction band is significantly higher because you deposit TiO2 by ALD method with a low temperature. So you have an amorphous nature. That's maybe a rutile or some other morphology, and then the injection efficiencies are significantly lower. When you do a tin oxide under normal conditions, the tin oxide has a lower conduction band. When you do by ALD treatment, the conduction band of the tin oxide is well aligned with the LUMO of the perovskite. So you can see with the tin oxide, the efficiency is 18.1% efficiency. It's significantly higher. So the band alignment for the electron extraction is a critical. So I show you another interesting data to show the importance of the band alignment in the whole electron extraction layer. So here is the perovskite, this inverted configuration. As long as you have a PCBM as electron acceptor, the efficiency is extremely high. The moment if you offset the band alignment, even 300 millielectron volts, the efficiency comes down significantly. So demonstrating the band alignment is very critical in this type of materials. I'm just running out of the time, but to show you the stability, we just go with without whole transporting material. You have this type of configurations, and this work is done at this university in Jeddah. The stability data is shown here. It's quite stable. Let's take the conclusions. Take-home message. If you forgot all my talk, what you should do is, if you want to start perovskite research, what you should do? You should have a 10% excess of lead iodide. You should have a mixed cations, 85, 15%. You should have a mixed anions, right? Then you can reach very high efficiencies of 20 if you engineer the materials, whole transporting materials. The band engineering is very important. As I mentioned, this is a team effort. We have an excellent team in EPFL with 4 people involved, 4 team leaders. Professor Andres Hackfeld is in the audience. Michael Gretz, everybody knows, he is a professor on Dyson solar cells. And I'm working, and Jack Moser is expert on the charge transfer dynamics. These are my PhD students, and I have a very strong team of postdocs. So I have external collaborations coming from various countries. These are the funding agencies. I'm really thankful for the various industrial partners and the European Commission and Swiss National Science Foundation. This is my group, and behind the group is Dyson solar cell panels involving my dice with red and green and orange dice. Thank you for your attention. I will be happy to answer your questions.
Thank you, Professor Naziruddin, for this nice talk. We have a few minutes for some questions. We will start from the lady, from the men's area, please. If there is no question, I will take the privilege to ask the first question myself. I can't see any. Is there anybody who wants to ask questions?
Your new HTM,
yeah.
Is that doped or not doped for the 20%?
Yes, that's doped.
It's doped.
That's doped. Sorry, I forgot to mention, that's a doped one.
Thank you.
But we have plans to do undoped with the same concept, having interaction with the perovskite, but come up with undoped materials.
Great. Thank you.
Yeah.
More questions? From the ladies? There is a question over there.
Thank you very much for your interesting lecture. Actually, I have 2 questions. First one, during your preparation for the perovskite, you make a annealing step, and if you at which temperature, and if you check the annealing, the temperature of annealing might affect also the morphology and hence affect also the output of your prepared solar cell.
Yeah.
So it's the first one.
It's a very interesting question. So I forgot to mention annealing temperature is very critical. And the thickness of whole transporting layer is very important. All these parameters are very important. The question is what temperature we anneal and how it influences on the performance. We usually anneal these films at 110 degrees temperature. The moment if you go a little higher than 110 or even 130, what happens is some of the methyl ammonium you evaporate and then you form a zone on between the perovskite and whole transporting layer, lead iodide rich zone. And we don't know the influence of this rich zone, but the efficiency certainly is not as good as when you sinter the film at 110 degrees temperature. The take-home message, sintering temperature is very critical, 110 degrees is necessary. If you go higher, then you have a problem with the defects.
So please, I have another question. May I? My second question concerning, you also used the TiO2 nanoparticle and TiO2 nanotubes, and you even changed it to SNO2. Did you try to use another semiconductor like zinc oxide maybe? Because there's different band gap, and from TiO2 maybe better.
Yes.
Thank you.
Again, the question is on the electron transport layer. We have used TiO2, we have used PCBM, we have used tin oxide. Did we use zinc oxide? There is a Canadian group, Tim, he has published over 17% efficiency using zinc oxide as electron acceptor layer. Personally, I will not encourage you to use zinc oxide given its instability of this material.
More questions? There, one question.
Dr. Nazaruddin, you are not saying to us what's happening to the hole itself when this lead is moving, and how you prove it's moving. I follow up you. Do you have some evidence that this lead is moving from one side to other? I mean, what's the relation between them? Moving the lead and the hole itself, what's happening?
Maybe, are you asking about the hysteresis problem of ion movement, or you're asking about the...
You say there is a lead moving in one of the final stage. So what's the relation between the lead moving with the hole itself?
Okay.
The perovskite hole. I mean, you have a hole jumping the electrons doing the
Yes.
entire circuit.
Yes.
So what's the relation between them?
Okay. So let me try to explain you. So you have a lead iodide HOMO levels. The positive charges are jumping into the whole transporting layer. Now, the excess of, if your question is directing toward the excess of lead iodide, and this lead iodide, what we think is having interface modifications with the TiO2 nanoparticles. It's nothing to do with the whole transporting junction between the whole transporting material and perovskite, right? Now, how the hole is migrating, and we are doing the femtosecond charge transfer dynamics to find out, to put your eyes in the material, what is the speed of this whole extraction. So we know the speed of electron injection into the TiO2, but we are trying to get the whole extraction kinetics using various spectroscopic techniques. So that we will probably publish soon. Thank you.
Okay, I will ask the question myself. How do you see the normal and traditional dye synthesizer solar cell materials, the organic dyes and the inorganic dyes, in front of the perovskite? Because, long time people are working on the DSC, and the maximum efficiency they reach is not up to 11%. Nowadays, we can see that the perovskite can be extended more than 20%. But the stability, I think, for the perovskite is much more. But there is another issue for the perovskite, which is the environmental issue. How do you think the traditional old work that's been done for the DSC is going to be for the future?
Yeah, these are very pertinent questions. The first question, probably I will start answering from his last question, which is environmental issue. Like a material scientist, and I see this as an opportunity. Yes, we have a problem of environmental problems with the lead. Can we come up with new materials which extracts lead significantly without polluting the ground? So I have a another big job to do, extraction of sensing the lead by sensors and extracting the lead by the materials which you design yourself. So I am thinking of a containment of the lead. Suppose if there is a leakage, suppose if there is a damage, how do you contain this material? So what you have to come up is the material which selectively is just like zeolite. Extract the lead into your container and then dispose of. This is one possibility. And now coming back to the first question, how do I see the DSC? There are two different technologies. The DSC has a beautiful colors, what you see behind this, and it integrates into the buildings. It gives you efficiencies, not very high, but it reduces your electricity consumption, particularly in the Middle East when you have a strong sun shining. So you use a lot of electricity for air conditioning. This acts as a filter. So you have a different application. For the efficiency point of view, I say I'm very optimistic that every communities will produce their own electricity, and we will see the way you are seeing the mobile phones, the grid-free energy generated on the spot. So you don't have to have a transmission lines, you don't have to invest anymore on these big supply lines. So locally you produce, locally you consume. So the consumers today will become the producers tomorrow. That's what I see in the future of the perovskite solar cells.
We have one more question. Last question. Well, if there is a question over there. Yeah. And
Is there a possibility to replace lead by another metal? Again, the answer can be yes, but inside answer can be no. It's the reason why I have mentioned yes. That gives me opportunity to screen all my periodic table, that I can write some proposals to get money, but from my heart, it's difficult. The reason I mentioned the electronegativity, it's very important. So what you have is a beautiful combination of 2.66 iodide, 2.33 lead, and that gives you the excellent ionicity and covalency of this bond, and that's the beauty of this whole material. And not only that one, you have a symmetry, perfect octahedral, and it's a cubic octahedral symmetry, and the three-dimensional material. All this, and spin orbit coupling, that's heavy add metal affect. All these properties, if you look at the periodic table, I may have a difficulties to replace other metal. But having said that one, there is a possibilities we can come up with other metals where environmentally safe metal like palladium, which gives you two-dimensional perovskites. And now question is, can I change the cations by having complementary absorption in the near IR region so that I can get whole visible spectral response in the two-dimensional perovskites, where I have to manipulate the cation, which absorbs complementary to the two-dimensional perovskite. The drawback of the two-dimensional perovskite is it absorbs below 600 nanometers.
okay. Well, at the end, we would like to thank you, Professor Naziruddin, for this nice talk, and a few announcements. First announcement is that there is a bag for Dr. Abul Qasim. Muhammad Abul Qasim, I think from Tanta University, somebody exchanged the bags with his bag yesterday. His bag contains some important documents. If somebody found it, please contact us or directly try to contact Dr. Abul Qasim. This is the first announcement. The second announcement, we will be back for our sessions at 10:30. So now we will have a break until 10:30, and then we will start again our sessions. Thank you very much.